So last time, so we're proving the Feynman-Rouget theorem. I will finish today. So last time we saw some basic tools of so-called additive combinatorics, Feynman homomorphisms, and also Plüniker-Rouget estimates. So the effect has been of Feynman homomorphisms has been to reduce the situation from that in Z, the integers, to that in Z modulo nz. So we'll be able to work in Z modulo nz. I have to introduce some basic tools, some more basic tools in additive combinatorics before we can really proceed. So I briefly mentioned Bohr sets, I believe, at some point. Let us define them formally. Very well. So forces and energy. So what do I mean by them? So reminder that when we're working in Z modulo nz, we can define a Fourier transform also in Z modulo nz. So this is self-dual. Whereas usually I write E as shorthand for e to the 2 pi ix. E of x is e to the 2 pi ix. So here I have minus psi x over n, and here I have f of x. So it satisfies the usual rules. So Plancherel, or Parseval, however you want to call it. So this has to be renormalized. Well, it's true as stated. Just let me make clear that by this is meant. So we need a factor of 1 over n here, you see? So this is easy to check. We also have the Fourier inverse theorem and so on. So all the usual rules of the Fourier transform. I'm just writing these things down so that the normalization is clear. All right. So let me introduce a concept whose definition does not involve the Fourier transform, but it can also be expressed very nicely in terms of the Fourier transform. So let G abelian though in fact we could do this generally if we were careful, but never mind that. So the energy of A and B, so it's the energy of the two sets in relation to each other. It's defined as follows. So it's the number of quadruples such that A plus B is equal to A prime plus B prime. So this is the definition. Note that so it's easy to see that this is one everybody with me here? So it's a convolution. Remember the convolution? So the convolution, the value, so this is just the indicatrix function, the characteristic function. So 1a star 1b at x, what is this? 1a star, so what is the value of 1a star 1b at x? of ways of the right x as a sum of an element of A and an element of B. So if I raise it to the square, it's the number of pairs of ways, if you wish, and if I sum it over all x, it becomes precisely the number of equalities.
It's not a set, but a count of...
Sorry? Yes, that's right, excuse me. Thank you. So this is just, I mean, this is the tautology, this is just shorthand, of course, is the L2 norm. The L2 norm squared is just the sum of the squares. But, yeah, by Plancherel, this is the same as the L2 norm of the Fourier transform, but the Fourier transform of the convolution is the product of the, yes, exactly. So this is ta-da. Oppa. Very well.
What we denote by L2 norms, both L2 norms.
The normalized L2 norm. So it's, of course, it depends on the.
We use the same notation.
This looks like very bad notation, but in fact it's good notation because there are really two groups, Z mod n Z and its dual, which is also Z mod n to Z. It's just that the norm is different. In one case it's normalized, and think of this as being physical. I mean, you know, the customary terms are physical space and Fourier space. I mean, the space Z mod n Z and its dual. So its dual happens to be Z mod n Z. Yes. But yes, we have to be careful. So, what the inequality is here? So the issues inequality is that this is, of course, bounded by A squared times B. Why? Because if you have two elements of A and an element of B, then they determine the fourth element in the tuple. Now, a little subtler. There's something a little subtler. So fairly easy. By the inequality that is called after Cauchy and always somebody else. This is pronounced Schwarz in English, but never mind that. We have, yeah, in fact, Cauchy, it's really Cauchy because it's for sums, but both Bunyakovsky and Schwarz, Bunyakovsky a bit before, in fact, proved it for, I mean, generalized it to integrals. It isn't hard. So this is just Cauchy Bunyakovsky, and this is now. Yeah, remember, this is the 2 is in the outside, and this sum just turns out to be A times B. Because it's just a sum of ways to write x as an element of A and an element of B, and you vary over elements of x. So it's just a number of sums of one of, I mean, the number of pairs A, comma B. And so, dividing on both sides, you get, so just to be very clear, you get that E of A comma B is at least A squared B squared over A plus B. Very well. So if the sum set is large, then the energy, if the sum set is small, then the energy has to be large. So if A plus B, or say A plus A, is barely larger than A, then E of A comma A will have to be very large, close to A cubed. Very well. So another important object, definition. So let rho be, and well, So again, you could define this for any group. So we will, the row spectre of f is just a set on which the Fourier transform is bigger than rho. Times the L1 norm. Of course, f hat of psi is always going to be at most the L1 norm of f, that is the sum of f or the so just a brief reminder. So it is just f of x, and in general fp is in physical space. In Fourier space there's a renormalization. Alright, so this is a spectre, and we also have Bohr sets. So for S, Z and Z, Fourier space really, and delta in 0, 1, the Bohr set, mind you, this is Harald Bohr, not Niels Bohr, very important. It's a set of all x's such that for every frequency in S, the absolute value of the fractional part, so it's clear that this means fractional part, right? Meaning the distance, so just to make sure everybody remembers this, well, this is always in fractional part. Yes, please complain. It's a set of all frequencies such that psi x is small, modulo n. Or if you wish, I mean, this could be stated alternatively as being E of psi x is close to 1. E of psi x over n is close to 1. Same thing. Very well. All right. So what is a Bohr set good for? So as I said, this means that E of psi x over n is close to 1. So if you're looking at a Fourier transform and you're looking at certain xi's, the xi's in S, which for some reason may be important, then whenever x is in the Bohr set, E of psi xn will be about 1. So you will have good control over certain terms of the Fourier expansion. So now comes a very important proposition. And the proof will actually remind you of some things we saw in the first class when we did Roth's theorem. So let xy be in z mod n z, and alpha is such that, so the energy is assumed to be large. So it's some alpha times x squared y. Of course, x squared y is the maximum the energy could ever be. So alpha is at most 1, but this is going to be useful when alpha is, you know, something like 1/100th or 1/10th or 1/3. So it's something to be used when the energy is relatively large. Well, for these two sets with relatively large energy, we have that a Bohr set is going to be contained in x plus y minus x minus y. So by now it's completely clear what this means, right? This just means a set of all combinations of the form an element of x plus an element of y minus x. Where what is S? S is the spectrum of x at level alpha, the square root of alpha over the just so that everything is clear. So alpha small would not be good, alpha very small, because alpha small means S large. The smaller the level, the larger the alpha spectrum. And if S is large, then the board set gets smaller and smaller. And of course, containing a small set is a weaker statement than containing a large set. So as I said, this statement is particularly strong when alpha is large. So,
this statement is not symmetric with respect to x and y.
no, but if you want to, if you like y better than x, then just switch them. Ta-da. So
the conclusion is symmetric, but the statement
x,
yes?
x.
S,
Ha.
X, okay.
There should be not x, but indicator of x.
What do they do?
Spectrum of the function.
Yes, that's completely correct. This is, you can see this as shorthand, but very good. So we know what. So I'm just going to restate the assumption by what I was saying here. And I'm going, so this quantity looks sort of magical, so I'm going to start setting S spec of x row, and row will be set later. It will be set to this at the end, but it will be set to whatever makes things work. So by definition, two erasing systems are not compatible. So by definition, x can be in the set if and only if the convolution is non-zero at x, and so what have I done here? This is just the inverse Fourier theorem, because this is just 1 minus y plus x minus y, correct? Well, not this, sorry, it's this. No, I lied. You have to correct me. It's not the same. Very well. But we agreed that, you know, that's that. The absolute value is due to the fact that you have x here and minus x here. All right. So what do we have? We have that for psi in S, as I was saying, what does it mean for x to be in the board set? So let x be in the board set. The idea is that for psi in S, actually, why do I have this omega? Omega is just going to be, yeah, let me just write this correctly. Everybody happy now? You should correct me. No, semi-intentional traps. Yes, that's right. So the point is that it would be nice to have a pen. So our task is we must show this is positive for x in BS16 for every x in the Bohr set. Now, when x is in the Bohr set, for psi in S, by definition, this is going to be about 1, as I was saying. That's what a Bohr set is good for. Whereas for psi not in S, what happens is that one small. Why? Because we defined S to be the spec. So that's the idea. You will have this contribution of these positive terms for psi in S, and then the other terms will be small by definition. These terms where psi in S will have this close to 1, and the other terms will be small. So that's the idea of the proof. Let me actually write it down in full. So very well. We just need so of course this is real, so it's going to be equal to its own real part. Well, if I take the real part, life just becomes a little simpler. We'll just have a cosine. And this is going to be greater than or equal to, well, you see, because this is in the Bohr set 1/6, then the angle is going to be at most pi over 3. Cosine of pi over 3 equals 1/2. It's just a conventional value. So this is, when psi is in S, this is going to be at least 1/2. So I'm going to have and on the other hand, minus 1n for psi not in S. Same story. In fact, you can probably finish the rest of the proof, but so try to do that in your heads while I erase the board. Just to make things easier to estimate, I will find my notes, which have just disappeared. Here they are. Just to make things easier to estimate, I will add terms to both sides to have it's helpful. One over 2n. Here I will not use, it's the same thing as I wrote here. Minus, so now I'm summing over all psi. So what do I have? So here I have the sum over all psi of this quantity here. So that's just the energy. And then I'm going to subtract the small terms. So this is just the energy. minus 3 to n, the sum. Well, and what is the most efficient way of estimating the sum over the elements not in S? Yes, let me write out in full. Yeah, it's actually best, rather than bounding this right away by alpha, it's best to actually first take the so I take one psi this thing out, but I leave the sum over here. Why? Because now I can bound this using Plancherel. And that, of course, what is the L2 norm of this? Yeah, except that there's the square root because yes raises to the square. So it's just the size of y. The good thing about functions equal to 0 or 1 is that they don't change if they are squared. All right, so this is at most then rho x squared times y. So hence hence you have which is of course its own real part, being real value. This is 1 to alpha x squared y, or rather greater than or equal to, minus 3 rho x squared y. So we said, so this is what motivates the choice of rho. We just want this to be positive, that's all. And get that's it. It's very simple. It's the same idea as in a step of the first day.
No.
Yep.
There should be not 1/2, but 1/6.
Yeah. 1/6. Where should I have 1/6?
Rho should be 1/6.
Hmm?
Rho is
1/6 square root of 5.
No, I'm afraid not. In fact, I'm even overshooting a little because this gives you. Wait, am I wrong? Ah, sorry. It's because I had this 3/2. I forgot. I wrote this wrongly. This is 3/2, not yes. And now it works out. And in fact, there's some room left over. 1/2 is not optimal.
Rho is square root of 5/2, yes?
Yes, that's what value that works. Square root alpha/2 squared is alpha/4. By 3/4 is 3 alpha/8, which is smaller than.
3/8 is less than 1/2.
Yes, everything's fine. Very well. So, by the way, all right. The way we will apply this, at least here, is that we are going to have a set such that this is almost times A. Then, as we were saying before, EAA by Cauchy-Bondiakowski is at least A3/C. So alpha equals 1/C. Thus, we said x and y both equal to A, and we have that this contains BS16. So now the question is, does this mean that this contains a large arithmetic progression? The answer will be yes. Because any board set, for s not too large, will contain a large arithmetic progression. The reason has to do with the geometry of numbers. So, in general, let gamma be in Z mod n Z, n prime, k in gamma, k is the size of gamma, and delta is just going to be a number between 0 and 1/4. Then, do you remember generalized arithmetic progressions? It just means arithmetic progressions to several moduli. And they are called proper if there are no repeated terms. I will even give you something for free. If Q is proper, if Q is an arithmetic progression, then Q minus Q is also an arithmetic progression. We will prove a bit more than just this. We'll also have, and it's useful for our purposes, Q minus Q is proper. At any rate, the main thing is that the board set contains a fairly large proper arithmetic progression. Of size, well, the dependence on k is not great, but at least it's explicit. So the bigger k gets, the smaller the arithmetic progression gets. So we have some interest in keeping the gamma small here. So proof. Let gamma, yes, write the elements like this, psi, they are frequencies. We can assume without loss of generality. Log just means without loss of generality. Как это по-русски?
Не умаляя общности. Не умаляя общности.
Не умаляя общности. Without breaking generality.
Yes.
That k is non-zero, and that for every I, the frequency is non-zero. Otherwise, it's you can just take out the zero frequencies. And again, a bit of triviality. For every I, let xi be an integer congruent to xi modulo n. Because xi's are elements of Z mod n Z, not of Z. It's just a representative of psi I. Is it hard to read?
Yes.
Okay, it's what I just said. I will no longer write on that part of the board then. Someday boards will clean themselves. The day has not arrived yet. So the idea is, lattices, everybody's comfortable with lattices. So a lattice is a discrete subgroup of, say, R to the n of rank n. So, the points, the corners here are two-dimensional lattice. So, let lambda be a lattice. It's going to be the lattice. It's the multiples of n plus Ri will be better than xi. plus the multiples of the vector R. So the covolume, everybody's comfortable with the covolume of a lattice? Okay, so let me write down what it is. In this case, the lattice is a subset of z to the k, so the covolume thing is easy. It's just the size of the finite group z to the k minus z to the k modulo lambda. But in general, the covolume of a lattice is defined to be the determinant of any basis of the lattice. That's independent of the basis. If you have a lattice like this, then if you take any cell here, then that's a covolume. Of course, you could also say, well, what happens if I draw it this way instead? I mean, the lattice is the points, it's not the lines. So I could say, well, you know, this gives me the same lattice. What happens then? Well, what happens then is that then the covolume is still the same, because the area of this is the same as the area of that.
Okay, can you just describe the first line? How you describe your lattice? Because
so it's the n times z to the k. It's just all the vectors whose entries are multiples of n, and here it's just all the integer multiples of the vector r1, r2 up to rk, where r1, r2 up to rk are just, sorry, I could see thing that you cannot see that line. It's just these representatives.
Okay, representatives
of the xi's, of the frequencies. Doesn't matter which representatives you take. The representatives are just mean elements of z which are congruent to them modulo n. And it doesn't matter which ones you took, because there's this big lattice just getting rid of those things. Very well. So, well, what is this? This is just, everybody comfortable with this? So it's just, you know, I have 3 subgroups. This is true even for non-abelian groups. And this would be, so what is the index of nzk in zk? So what is the order of this finite group? Yes, n to the power k. And what is the order of lambda modulo nzk? So there's just this one element which is not there, but its nth multiple. So I should specify n is prime, yes. So its n multiple is going to be there. So this is n. And now, how many people know Minkowski's second theorem?
If you formulate it.
Very good. Maybe it's called Minkowski-Wundziakowski. No, actually, there's a funny story related to that. English people say that somebody did the geometry of numbers at the same time or slightly before Minkowski. But never mind that. So they will always insist that H.E.J. Smith or something like that also did this sort of thing. But for the rest of humanity, it's Minkowski's second theorem. So for any lattice lambda, okay, and any bounded convex subset K, big K, that's the K, with K symmetric. By symmetric, I just mean symmetric around the origin, i.e. K is equal to minus K. So what's going to happen? First, I would like you to get a clear picture in your heads. So I have this lattice, and I am told what its covolume is, and I have some sort of blob, but at least it's a convex symmetric blob. So I haven't stated Minkowski's first theorem. Minkowski's first theorem just tells you how large the blob has to be for it to be guaranteed that you're going to be able to find a point in the lattice other than 0 in the blob. The second theorem is stronger. It tells you not just how large does it have to be to contain one element of the lattice, but 2 linearly independent elements of the lattice, 3 linearly independent elements of the lattice, and so on. So it tells you that lambda 1, well, I will explain in a minute what lambda 1 is, and lambda 2 and lambda k, that their product is at most 2 to the k times the covolume of lambda divided by the measure of k. Mu of k is just the Lebesgue measure. Is this clear? So the right mess, or mer, if you prefer.
And lambdas
I will define them. Where lambda I, which is really a function of k and the lattice, this is a so-called ith successive minimum. Is a inf overall positive lambda. It's a, well, basically, if k is closed, it's a minimum. Infimum, также infimum по-русски. Да? So it's the least number, basically, such that lambda k contains I linearly independent vectors. Of lambda. Very well. So it's by how much you have to scale down things, so that by how much can you scale down things so you still contain k linear independent vectors. So these are increasing numbers. Very well. So what do we have now? Well, it turns out that a Bohr set gives you a nice lattice. And a nice convex subset.
We don't discuss the proof, yes?
No, we will not give the proof here. I mean, it will take a while, and some of you have already seen the proof.
What?
Have you seen the proof?
Well, I have, but
Well, I decided not to give it. I mean, we can give it. We can do it some other day, but I think it's sort of standard. Fine with everybody? Do you believe it? All right, that's important thing. It's a result that is used a lot, for example, in algebraic number theory. And whenever you have lattices, it's elementary. And doesn't take too much time, but it would probably take us a good half hour. So I think we'll leave it out. And as the name indicates, it's more than 100 years old. So we will not discuss the proof. We'll let K big K just be a cube of size 2 lambda n around the origin. Correct? The L infinity norm is just the maximum. So So, yes, so by definition of successive minima, there exists a basis, just k consecutive linearly independent vectors generating lambda, such that this is true. Well, in fact, it's just from the definition, you get k linearly independent vectors, and then it's fairly easy to get them into bases.
That's a good question.
Yes?
This equality on the right board gives you some estimates for lambda 2. Say if lambda 1 is very small.
Yes, it gives you some estimates, yes, by using the fact that these are increasing. So it gives you some estimate for lambda 2. But it's often most efficient to use the inequality as is. Yeah, but there may be better estimates for lambda 2, I don't know off the top of my head. So you can get some estimates from lambda 2 just by using this. But they may not be the best estimates you can get from lambda 2, I do not know. So, write each bi as so we write each bi, as we can do, as something in the multiples of n plus a multiple of the vector. So all of these are elements of z. Since bi is in lambda ik, we have that, of course, bi divided by n is at most, well, fractional part, is at most lambda I delta, just by definition of what k is. So bi divided by n has to be close to the origin. And so we have that the absolute value of the fractional part is of course just Ri xi, because we can reduce modulo n, or unreduce really. This is at most what? This is what do I have here? Wait. There's something I don't like here. Yes, this is just the L infinity norm. So this is just xi. Well, no. Of course, it's just a particular case. It's j type, and this is at most lambda I delta. Xi is just, the bar just means modulo. So this means that, I mean, what did it mean for us to have this k? This means that we have a good control on the fractional part of our frequency times xi bar for yes, for the xi as written there. But what will this mean? Then we will also have a good control for any low multiple of xi, and for any sum, any linear combination of such things. So we define the generalized arithmetic progression in z mod n z, q equal to mu1 x1 plus mu k xk, where these mu's are just integers such that this is at most this. Then I claim, by what I just said, Q is actually contained in the Bohr set. Why? For every psi j in gamma, we have that the fractional part of psi j times this linear combination is at most so this is just by definition here. The mu i's are at most 1 over k lambda I, so this cancels with a lambda I, you get 1 over k, some have a sum of k terms, 1 over k each, so you just get delta. This is what I was just saying, because each of these are small, any small linear combination, meaning anything in the generalized arithmetic progression, is going to give you something less than delta. And that's what it means to be in the Bohr set, because it is true for every j. Very well. Now we just have to do two things. We have to estimate the size of Q, and we have to show that Q, and in fact Q minus Q as well, are proper. So how do I estimate the size of Q? It is here, not before, that we use Minkowski's second theorem. Because this is just by definition, there is at least that, multiplying all of these things. And so, by Minkowski's second theorem, this is so the product is at most 2k covolume, but the covolume we saw before is n to the k minus 1. The measure of k, well, that's just a cube, so it's 2 delta n to the k. So this is 1 over delta k to the n. Hence, Q is larger than delta over k to the k n. All right. And now we just have to, so this gives you the upper bound, the lower bound I promised you. So Q is not too small if k is not too large. Now I just have to show you that Q is in fact proper, even Q minus Q is proper. This turns out not to be hard. So proper just means that if we have two different things written in this way, then they are in fact different elements. So Q is a proper product, I claim. Let's do that. So, suppose that you had an equality where these mu's are not all identical, then of course you have, well, we leave this up to x1. This must be an element of n to the set k. Moreover, we also have that, how much is the absolute value of this? Well, we said before, in fact, not just the absolute value, but the L infinity norm, so the maximum of the absolute value for the coordinates. So we said before that this was, 2k lambda I delta n. It's just exactly what we did before, pretty much.
What is B? What is X?
Where did they have B? Oh, so excuse me. X, B is X. Very well. So everything's fine here. This is at most 2 delta n. And this is less than n, because delta was less than 1/4, in fact. So what happens if you have an element, all of whose entries are multiples of n, but all of whose entries are also less than n in absolute value? In one dimension, if you have a number that is divisible by n, but which is less than n in absolute value, what is it? 0. Yes, it is 0. Actually, I must emphasize that this is about the most common trick in the affine geometry. So it's a key fact in mathematics. It relies on the even more basic fact that if a positive number is bigger than 0, if an integer number is bigger than 0, it has to be at least 1. There's a big gap in the integers. All right. Which is what we wanted to show. And yes, in fact, ditto for q minus k, because then you have that 4 delta n is smaller than n. So in q minus k, it's the same story. Q minus k is an arithmetic progression just like this. It's just the coefficients can be twice as large, positive or negative. All right, so we're happy now. So what is the state of affairs so far? Let me just summarize. So we already passed from z to z over nz, but let me just say that. So this is a summary of the situation. We have that, starting with the assumption that A has small doubling constant, the energy, this was easy, is large. And then we showed that there must be a large Bohr set contained in 2a minus 2a for S the spec. And then we showed that there must be a Q containing this, where KQ is a proper generalized arithmetic progression of size at least 1/6k to the k n and dimension k. K here is just k is the size of S. Very well. So first of all, we would like to get an idea of what k is. That's not hard. So there's an easy bound for k. A is the sum, as we have just a couple of times, of 1ax squared. So this by Plancherel is just 1a hat xi squared. And this is at least what? This is at least the value of the sum restricted to s. So it will be s over n times a over 2c squared. Bunjakowski, rather. Oh no, no, Chebyshev. Yeah, well, yeah, I suppose. Yes, but it's spelled out, so it's nobody's. It's the same. Yes, you could say it's Chebyshev. Yes. And so, just dividing, we get that S is at most 4c times n over a. Very well, so at least we have an explicit bound for k. So we have shown now that 2a minus 2a contains a large arithmetic regression Q. Now we just have to show that a few copies of Q cover 2a minus 2a. This turns out not to be hard. And in general, it's a general feature, as we will see, that if you have a set A that grows slowly, A plus A smaller than C times A, then if A contains something large, then A is covered by few copies of that large thing. So Ruzha is covering them. Ruzha's name is pretty much all over the place in this. Again, something that is quite useful in additive combinatorics, and there is an analog for non-abelian groups, but let us state it for G abelian. A, B, and G. So there is always an R in A of size at most A plus B divided by size of B, such that A is contained in the translates of B minus B plus R. So this tells you that if you have a set B such that A plus B is not much larger than B, then A is contained in few translates of B minus B. So first a little definition will help us. Say R in A is B free if for all distinct Ri, R2 in R, R1 plus B does not intersect R2 plus B. So what we're going to take, what we're going to do is we take a maximal B-free subset. Just to be clear, so in English, we say maximum when it's unique, which it may not be. Maximal, it not be unique, but there's always a maximal, or at least one maximal set with a given property. Just means that you cannot add anything to it. So then, first of all, I claim that A is indeed covered by R plus B minus B. Why? If there were an X in A that were not covered, then what could we do with it? What could we do with that X? You could put it into R, so R would not be maximal. B-free, sorry. Right? Because if it were not B-free, it would mean that X plus something in B is equal to some little r plus some other little b. And so, well, this will be violated. No, this would be violated, yes. Because X would be r plus one little b minus the other little b. So the other thing is that because R is B free, you have that yes, R times B is equal to R plus B, the cardinality of R plus B, because these are all disjoint copies of B. But this is contained in A plus B, because R is contained in B. Okay, that's it. That's the proof. Ta-da.
Okay. And what did you say about non-abelian group?
Oh, we're not going to use this thing about non-abelian groups, but this, like many other little results in additive combinatorics, you can still make it work over non-abelian groups. You just have to be careful about where you put the pluses and where you put the minuses, okay, which we aren't here.
Okay.
Now, so we're not going to apply this right away, but if we applied it right away, we would get a version of Feynman's theorem over Z mod n Z. So we had Q in 2 minus 2a. We also have that a plus Q is, so Q is in 2a minus 2a, so this is in 3a minus 2a, which by Plunecker-Ruja would have to be in c to the 5 times a. And we also have that Q is at most 1/6k to the k. So, by Ruja's covering lemma, so this is not our final theorem, but it's a good theorem. It's Feynman-Ruja, not in Z, but in Z modulo n Z, and for large subsets of Z mod n Z. Otherwise, it's not good. Meaning large in relation to n. So let A be, of course, in Z mod n Z. A plus A at most C times A. Then A is contained, we have just shown, in at most c to the 5 times 6k to the k n over a translates. By translates I mean cosets of q minus k, which is an arithmetic, a proper arithmetic progression. So, and how large is this? Because it would not mean anything if it were huge. It's Z mod n Z is also a proper arithmetic progression, big deal. But no, it's not much larger than A, because you have that since Q minus Q is contained in 4A minus 4A, the size of Q minus Q is at most C to the 8 times A. And here, of course, as I was saying before, K is for C. So in Z mod n Z, if you have a subset which is not much smaller than n, a subset A, and it fulfills A plus A smaller than C times A, then A is contained in not too many translates of an arithmetic generalized proper arithmetic progression that is not much larger than A. And that's what we want for Z. It's a harder result for Z. So let us do it for Z. So recall that we actually have A in Z, obeying this. So yeah, so this is combined Ruja-Feynman, because it's Ruja's proposition from last time on Feynman's isomorphisms. So let me see. Well, we choose any prime n between, well, you know, Bertrand's postulate, between k and between m and 2m, there's always a prime. So we choose any prime. Then, by the proposition from last time, there is a subset with a prime bigger than a to the a over 16th, and the 16 isomorphism. By 16 isomorphism, I mean a Feynman isomorphism of order 16. 5 from a prime to z more than z. All right. So what do we have? So clearly, a prime plus a prime is at most, I mean, it's contained in a plus a, so it's at most Ca, which is at most 16 Ca prime. And so, an isomorphism is in particular a bijection, so it does not change the size of things. So this is well, and because it's a 4 isomorphism, being a 16 isomorphism, you also have that this is phi a plus a prime. There are no phi is not creating any coincidences. Is this clear why this is true? In general, in fact, I think being a 2 isomorphism is enough here. Yeah. This is just what it means. You send x plus y to, if x plus y is equal to z plus y, no, if the image of x and the image of y is equal to the image of z and the image of y, it's because they were already equal to begin with. And vice versa. So this is, because it's a bijection, this is a prime plus a prime, which is at most 16 c phi a prime. Again, this is the same as the size of a prime. All right. Happy so far? So we will apply what we have done so far, except for the last step. So we don't use Rouget's theorem, Rouget's lemma here until the last moment. So by everything else, this set contains, you know, we apply what we before we said A in Z mod n Z. Now phi of A prime is in Z mod n Z. So we apply, and it fulfills the condition, right? Phi of A prime is of small doubling. So by our work so far, this contains a proper, and moreover Q minus Q is proper too. Of size at least 1 over 6k kn. And of course this is at least 1 over 6k. Let's just be grateful. Size of A. Where what? Well, what is k? Well, k, the expression for k, that is S, that we saw before, involves n over the size of the set, right? This 64 is just coming from all of these 16s and so on. But fortunately, we had that, thanks to Rouget's proposition, and it's not, we can take it not much larger than A, as we saw above. So this is 16.4c times 2c16a you divide by 16, which is at most, well, this. So it's just a constant times the power of c. It's good. It's not too large. It's pretty large, but not that large. So it depends only on c, and it's polynomial on c. So since phi is a 16 isomorphism, it extends to a 4 isomorphism on 2a minus 2a, and a 2 isomorphism on 4a minus 4a. Thus, phi inverse q is an arithmetic progression, and moreover, both it and phi minus 1 q minus are proper. Why? Well, it's because two isomorphisms preserve arithmetic progressions, and they also preserve their properness. Let me just write this out in full. I think I said it the previous time. Two homomorphisms, in fact, preserve arithmetic progressions. Why? It's very easy. You see, this is f of everything, but with Rn minus 1 here, plus Yn. And so, because f of x plus y is, well, you will see. What do we have here? Have I just said something very, very silly? No, I think this is correct.
So
I want to write, yes.
What's the problem?
No, I just want to show that f preserves. I was saying that I was reminding you of how f preserves two homomorphisms preserve arithmetic progressions. So two homomorphisms, I remind you, are mapped such that x plus y equals z plus.
By something like a plus b equals to c.
Excuse me?
So what is arithmetic progression? Yes. That,
Yes.
Three numbers a, b, c are in arithmetic progression. If
Yes.
a plus c equals
That's right. That's in the one-dimensional case. So in the one-dimensional case, of course, these are generalized arithmetic progressions. Yes, I think. Yes, that's the idea. The question is what the equality was. I think it's going to be just about the same, but.
Some of the same equalities, but for what numbers?
Yeah. Yes, because I wanted to write. Yes, I wanted to write this, but of course it's not quite true. That would be a homomorphism. So this is not what we want. What we want?
No,
this is not right.
To increase only one coefficient r. I mean, if you write r1 minus 1, r1 plus 1, and
What?
so I mean 2f of x plus r1 y1 plus blah 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 equals f of x plus r1 minus 1 y1 plus blah 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 plus.
That's what I'm doing. We're almost there, but I think there's something missing here. So, I mean, it's clear that if I put here f of x, then this is true. Correct? Yes, but then we are done. because all we need.
Yes. I see. The last efficient. Yes. Yeah, it should be enough. Yeah.
Yes, because this is fixed. So that's a fixed increment every time we increase R1. Grr. All right, very well. And if it's to isomorphism, it also preserves properties. Which is what I'm using here. All right. And now we are going to use, finally, the covering lemma, which I am about to erase, of course. Because we have that this guy, phi inverse q, is contained in 2a minus 2a. It's also fairly large. Clearly, phi minus q is contained in 2a minus 2a. That's just how we define things. And so phi minus 1q plus a is contained in 3a minus 2a, which is at most C5a by Pluneke. And we also have that phi minus 1 over q is q, because phi is a bijection, is at least 1 over 6k to the k times a. We apply Rouget's covering lemma. And we obtain that in at most this many translates of phi minus 1 over q minus phi minus 1 over q. All right. So since phi minus 1 over q minus phi minus 1 over q, so since this is contained in 2a minus 2a, 2a minus 2a, this is at most 4a minus 4a. So this is C8a, again by Pluneke. All right, so we have obtained that A is contained in not so many translates of a proper arithmetic, generalized arithmetic progression of given size and blah 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 blah. So we have finally proven then the Freiman-Rüger theorem. With not terribly good bounds, but they are still better than the first bound set. Over Z. Though much the same proof, well, not, in fact, it's not trivial to generalize it to abelian groups, but it can be done. So, let me just repeat the statement of what we have proven. Let A be any finite subset of Z, A plus A smaller than CA. Then A is contained, let me put it this way, in the union of at most e to the d1 over c translates, meaning cosets. Как cosets по-русски? Class. Proper generalized arithmetic progressions of dimension d2c and size at most, well, d3c, where, what are the bounds we have given? So d1 over c, d1 of c, for us was 5 log c plus, well, I'm just going to write it out, but it simplifies quite easily. It's at most a constant times c17 log 2c, say. This notation is clear, right? When I write less and less than, it's the same as f is of O of g. And d3 of c is c of 8. All right, well, so we will discuss now some improvements that have been done to this d1, d2, d3 over the years, because these are pretty much the values as they stood some 15 years ago. They have improved, or say 12 years ago. They have been improved since then. But first, we should also discuss some variant forms, because depending on what form you give, there are more or less equivalent forms, but in some forms, what we have got nowadays, or in fact what we had 5 years ago or 4 years ago, looks optimal, but really isn't, because in other forms it's clear how far we are from optimality. So other forms of the theorem. Let me give you first a truly equivalent form. Well, so some prefer to have, I cannot raise this much anyhow. So some people don't like a generalized arithmetic regression so much. I mean, it's something very nice, but there are nicer things in the universe. So in fact, some people just prefer to have just phi of let me write this some other phi to make clear it's not the same phi as before, where phi is just a homomorphism phi from some zk to z injective on lambda k. Lambda is a lattice, and K is a convex set. So some people find that this is more natural than a generalized arithmetic progression. It's a matter of taste. If you choose to work with this object, then the proof actually becomes shorter because you don't use Minkowski's second theorem. That's all. All right. So same proof without Minkowski. So this is what you will find, for example, in Sanders' survey paper. His latest paper on the subject from last year. Then there's the other, more classical form of the Feynman-Rouget theorem. It's when you don't. Some people don't like to say that A is contained in the union of so many translates of a proper arithmetic progression. They prefer to say A is contained in an arithmetic progression. Period. So. By one arithmetic progression. So one can get something trivially of this form from something of that form, but the bound would be horrible. So you would get trivial from this form of the theorem above. You would get a progression of dimension e to the d1. It wouldn't be proper anymore, but the worst thing is that it would be this would be the dimension, which is really huge. Because all that I'm doing here is I'm just adding every element, you know, this each class, each displacement is for the form some x plus q. So I just add every single x like that to the basis of q. Right, pretty stupid, but it does give you qualitatively a result of this form. With a horrible dependence. However, one can do much better. But, you know, in the earliest versions of the Feynman-Rouget theorem, in fact, I think Feynman did not give an explicit dimension of d1, d2, d3, and Rouget's original bounds were quite bad. So one can do much better. This is about 12 years old, perhaps. Chang's covering lemma. And again, like many names in this theorem, this will, as we will later see, this name has multiplicity higher than 1. She did more than one thing. Mei-Chu Chang. So this is something like Rouget's covering lemma. Let G be abelian. A being G. A plus B. Sorry, A plus A at most CA. A plus B most LB. Then what? Then there exists T at most logarithm of CL. So this just means the smallest integer larger than or equal to C. And S0 st minus 1 kt. Yep, there are, well, RT, sorry. So sets of A. All of them of size at most 2C. So you have logarithmically many smallish sets, well, pretty small sets in fact, such that A gets covered by B minus B, not plus one set, but plus S0 minus S0 plus S1 minus S1. So by several smaller sets. So as you see, this is like Rouget's covering theorem, but it is much more structured. So given as some set R, it's a linear combination of really small sets C. And this is useful because what happens if C is small but L is really large? The results from Rouget's covering lemma would be very large. But here the dependence on L is only logarithmic. So we're fine. So the proof is a little bit like that of the Rouget covering lemma. So proof, So we'll give it like an algorithm. Well, we assume, without breaking generality, to use Russian expression, that C is an integer. So we set B0 equal to B. For I greater than or equal to 0, let Ri be a maximal Bi free subset if Ri is already small. We set t equal to I and stop. So stop as in a computer program. If not, we proceed with a loop. Otherwise, let Si be a subset of Ri of size 2c. I do not care which subset. Some subset. Let Bi plus 1 be Bi plus Si and continue. All right, so clearly Bi is going to be 2c to the, because all of these things are free, you see? So as I said, so yeah, you remember what being free meant. It meant that, so Ri is such that any Bi plus R and Bi plus R prime for an R prime distinct elements of Ri are disjoint. So it's all disjoint copies. So Bi is at most R times, Bi is, the size of Bi is the size of R times the size of Bi minus 1. So I'm just repeating these I times. However, you also have that Bi is B plus S0 plus Si minus 1, which is contained in B plus II. And so, by Pluneke, well, first of all, obviously, this is less than, because to be contained means to be no larger than. So this is by the Russia triangle inequality. At most B plus A divided by A. And here we use Pluneke, that is Pluneke-Russia. L times Ci plus 1 times B. The L just comes from here. So what do we have? Hence, 2Ci is at most LCI plus 1. And so 2I is at most LC for all IT. Hence, T is most log 2 LC. That's it. And now we're going to use this new covering lemma. So we apply Rusja's covering lemma. No, sorry, Chang's covering lemma with phi minus 1q instead of b. So what are the bounds for C and L that we have? So we have a plus phi minus 1 over q is at most, again, 3a minus 2a, which again is at most c5a. Well, yes, which is at most, of course, LA with LC5 CKK, which is really large, but again, the dependence on L here is very good. It's logarithmic. Just a logarithm in front of the L. That's a good thing. So we get it is this that will allow us to get some sort of decent dependence in the classical form of the theorem, where everything is covered by one large arithmetic progression. We get right away by using this covering lemma instead of Rouget's that we can cover A. So we apply Chang's covering lemma and get, so with A as A and with phi minus 1q instead of B, and get that A is contained in q plus q minus a0 minus a0. By the way, this will not actually be proper most of the time. To get properness here, you have to do extra work. We will not get into that. So it's an arithmetic progression of dimension almost what? Well, k, which is a dimension of q, or q minus q. And then it's just the size of these sets, because these are linear combinations, just with coefficients plus and minus 1. So you have t plus 1 to c, and if you carry everything out, this ends up being c18 log c plus 1, say. And the size of the progression, well, you can also do this. It's not hard. It will be c for a, which is the size of q minus q, times 3t to c times 2c plus 1, I think. No, 2c. And this at most e to the of c log c plus 1 a. So we obtain finally, so Freiman-Rouget old formulation. So let A be a finite subset of Z, A plus A and no CA. Then A is contained in a generalized arithmetic progression of dimension at most d of c and size at most f of c times the size of A, where, well, what are the bounds we have got? D of c is at most c18 log c, let's say log c plus 1, to be safe, and f of c is at most EO of c, we don't need this, c18, one gets to the 18, bookkeeping, but log c. So if you wish, you can put the c here. All right, again, not too good, but a lot better than what we got before. because this is the dimension is polynomial at least. All right. So now that we have got the two forms, we have got only a few minutes left. Let me just discuss informally some of the ways of improving this. So I will not have the time to go into the details of what each person did. So let me just put the names on the board. Do you want me to type up the notes? Do you want me to type up the notes for the course? Too late to them? Well, I mean, it will take a time. It will take some time.
Not
but
against the sure that
okay. It's a matter. I will try. I don't promise, but I will try. So the same Chang, there's a spectral theorem. So what did Chang do? So one thing is that. So I will say it because it's something very nice. Well, no, let me not. Let me just say that the spec X row is structured, meaning it's contained in the span of gamma small, relatively small. What do I mean by the span of something? Span of gamma is the set of all linear combinations with coefficients between -1 and 1. So this helps a lot because this means that you can that your Bohr set contains a Bohr set defined in terms of gamma instead of S. Gamma will be much smaller than S, and that really helps things. So I will this will be like a scoreboard at the end of a game. So what you get here, you get a much better power. You don't get c to the 18th or whatever it is. You get c squared. So these are the bounds that you will get. I was asked for more precise reference last time. So this is what you get in this position, Ben Green's structure theory of set addition, which you can find on the web. If you want me to type up the notes, if any of you is good at later and can type up a draft and then I can correct it, that would also help. So Schoen, and these are Schoen that's just 4 years old. So he managed to optimize a different step, the one where we passed from A plus A to the energy. He managed to show that you can find subsets in A and A which have much larger energy relative to their sizes. So I will not be able to write exactly what he did again, but he got d of c, co of log c, that is, it's almost c, so c to a power tending to 1. Little o, it's clear what that means, right? It's something tending to 0. And f of c is the exponential of c e of log c, which is exponential. So this is in a paper by Schoen that has a title of Near Optimal Bounds. So the paper is called Near Optimal Bounds for Feynman. So these are near optimal bounds, but only for the classical, the old form. So for the old form, it's actually quite easy to see just by taking a completely random set of n things, that the best you can do is C and C here. Because if A is a random set of C things, A plus A is going to be at most C times A. However, you're not going to be able to give it any structure. At the same time, if you take the new form of the... so what does Schoen give for the new form? So this is still Schoen. It gives d1 of c, it's at most e of o of log c, and this is still far from optimal. So let me just give you, on the one hand, the conjecture of what the best values should be, and on the other side, the best bounds known for the new form. So the conjecture, which goes by the name of the polynomial Freiman-Ruja conjecture, says that d1 of c should be a constant times log c, d2 of c should be a constant times log c, d3 of c should be a power of c. The best result known, so this is Sanders, different forms from and based on Kreutzig, which is a theorem in Fourier analysis, really. You have that, which is based on Hengchin's inequality, but applied in a very clever way. So he gets basically the cube of log c. So we have two options, in fact, at this point, and we can take a vote, or at least I can consult you. All right. Or he can also do log c to the 6, log c to the 6, and c to a power. At any rate, he gets fairly close, but not quite there. So we can just close this chapter and finish Freiman-Ruja and go on to the large sieve next time. Or we can actually, I could actually try to give a class summarizing what Sanders did. What do people prefer? I'm consulting you, I'm not forced.
I think that some popular summary or Sanders work would be great.
What do other people believe? Okay, so what I will do then is I still have to convince myself that one can actually give Sanders in 2 hours. If I convince myself, I will give it to you. Otherwise, we will go on to the large sieve, which is a more classical subject in analytic number theory. Everything we have done so far is what usually goes under the heading of additive combinatorics.
Do we have time for both?
Possibly, in which case the order is commutative, right? Possibly. Yes, more almost.
Try, of course.
We will see. There are actually some ideas in common between the large sieve. One thing we can do is we can do the large sieve, and after a break, if people haven't forgotten, and if we have time, we can go back to Sanders' proof.
Okay.
Well, I will prepare my notes and I will see how I can structure things. But I think people are interested in what Sanders said. All right.